So you're recording my whole coffee conversation. Nothing private here. It's all on video. Okay. Maybe I'll put the, there. Yeah. Excellent. All right. Okay, so I think the next thing that makes sense to go through then, we loaded a sample data set, so we're getting rolling here, is this Ttest walkthrough. And I chose this just to basically give you an idea about the basic functionality and how you can create a very simple script that does a kind of a complete analysis. So again, on the walkthroughs on the website, it's there in the HTML with the output, I believe. And then here I'll load the live script version. That wasn't it. It's the other one. That one. That. And again, this is also in the GitHub, so you have the original code and then the HTML in there too, right in the repository. And I just took stuff from the repository and plopped it on the website, which I hope to continue to do. All right, so here it is. So this is the group analysis. And the idea is, I mean, this is the basic kind of result that you would put in a paper, right? You would do this group analysis in whatever way. The one sample t-test is the simplest way. Are the subjects significantly different across 0 in their reappraised versus look contrast? And then you would, show the map, print a table with the coordinates on it, write your paper, and say, look what's activated during reappraisal. Now, of course, that's not the end-all, be-all, but that's a lot of papers. That's kind of the bread and butter. And if you can do that easily, then you can go on and do more fancy stuff. So the idea is, this is the entire analysis. So this is all the code you need to do that, which is nice. So then if you have that data set, right, if you're writing a paper, you have the group data set, which is super lightweight, and you can share it or send it to anybody, along with this script, which is, 5 lines-ish, 6 lines of code. Then you could reproduce the paper figures. And then the other good thing is then, if you have that script packaged that way, and then your nice, friendly reviewers say, well, what would have happened if you had done this little thing instead? Or like, drop subject 16, or whatever, include the motion parameters, whatever. So then you have to go back and redo everything. But at this stage, at least, then, it's all scripted, so you rerun it, and you can regenerate all the figures easily. That's the idea. So this is the entire analysis, and let's just walk through it. Okay, with a couple minor additions. And you should be able to do this alongside me, I hope. So go for it. The first thing we're going to do is load this data set in. And by the way, let me also say, I think I might have another example. No, I don't. Some of the other walkthroughs have an example of, like, if you're not loading this named set, what do? Basically, you take any set of nifty image or analyze image file names, right? So you got to get the file names into Matlab by listing the files somehow in SPM, or we have a tool called file names or whatever. But once you have that matrix of the file names, that array of file names, you just, I'll show you this later, do fMRI data on that list of file names, and it creates the object. I should probably show that to you. So actually, and then we'll do the rest of it. Okay, so this is it. So this is the simple way. One line of code to load the data set and prepare it. And maybe it ran everything. Oh, it just ran everything again, interestingly enough. And that data set is called image object. And image object, oops, I just ran everything again, I think. Okay. Image object is that the same data set that we've been working with. It also has the file name. So this is the idea. So if you have a matrix of file names like this happens to be one 4D nifty image file. and it was gun zipped. It'll read it gun zipped or not. But we should be able to do like, see if this works. Yep. Okay. It did. Oh, it couldn't find the, yeah. Anyway, it said it couldn't find the files because they had these like commas with the SPM image listing file format, but I can get rid of that warning. But there it is. So there's the data set again loaded in. I'm going to go through more about the objects in more detail later if we have time. But for now, let's go through the analysis. Okay, so we loaded it in. Now you also know how to load in any set of image data you want to. You don't have to use this command, right? You just use fMRI data on the list of file names. And okay, so now we're going to do a t-test. So this is it. So we do t-test on that object. So we've done it. That's the whole brain voxel-wise one sample t-test. Now I can do, I'm going to go off script here, but I can do things like orth views, t, and there's my t map. So that's the group map, unthresholded. I can do montage t. Oops, I didn't make a new figure. There's montage t, without a new figure. Okay. So that's unthresholded. Now, what is t? Well, t is another kind of object, and this is a statistic image object. So again, I've got like 5 types of objects, right? fMRI data is one type, statistic image is another type. And now I can do stuff with this statistic image object, right, which contains maps, one or more statistic image maps. The difference between that and any other fMRI data set is it's got p-values attached, degrees of freedom, things like that to keep track of so that you can actually work with it as a statistical inference test. Let me go back for a second here. So we just did the t-test. And now, let's look at the results. Okay, we did orth views, t. We got the unthresholded results. But now we want to threshold it. Right now, these tools, you can do false discovery rate thresholding, or you can do uncorrected thresholding. And I thought we had some of the facilities to do this cluster extent-based correction, but I'm kind of off of that right now because we started publishing papers why that's wrong and misleading a lot of times. So I think we're just going to leave that one aside. And then there was this paper that some of you might have heard of, this Eklund paper, Eklund 2016 with Tom Nichols, where there's some problems with cluster extent thresholding. So I probably won't proceed ahead and worry about that. But let's threshold it with false discovery rate 0.05. So now I've done it. I've applied the threshold. And now it says there's 27 contiguous clusters and what their sizes are from 1 voxel to 1,400 voxels. 2,500 significant positive voxels. The minimum p-value across the whole image is that, negative 37 voxels. Minimum p-value. So it just gives you an idea about what you got in the image. But now, if I bring up the orth views again, now I'll get the thresholded image. So those are my thresholded results. I can re-threshold it too, incidentally, right? So that's the idea here. We can apply an extent threshold too, like this. So let's do a couple different things, right? Let's look at it with the extent threshold. Okay, now there's 9 clusters of at least 10 voxels. We can look at that, what that looks like there. Okay. We can create a montage of it. Now it'll plot the thresholded one. So let's do that. So now I'm going to create an actual figure first. There. That create figure just says create a figure with this name. And that's my function, so it reactivates the same figures if you pass in the same name. It's just convenient instead of creating new figures all the time. So there's the montage with the thresholded results. So if I'm happy with that, I could put it in my paper. I could put it in my supplementary materials. if I want to just show one little slice. I kind of really like the idea of showing all the slices because you kind of want to see what's the extent, like what's the activation really look like. And if I'm an analyst, I might do two different things. One is, which is I think is okay, one to show the final results where I want to make sure that I'm correcting within gray matter only, for example, you know, because I don't have to correct across the ventricles, and then show those results in the meaningful areas. I also want to look at things at a very liberal threshold, which is again helping me diagnose if there's some weird stuff going on in my images. Like, do I see activation in the ventricles, for example? There's several ways of looking at that here. We'll come back to that later. But one of the ways, just for illustration purposes, is let's say I want to look at this at an uncorrected threshold of like 0.5. Now I've got a lot of stuff. Okay. Or let's check out the montage. Oops, didn't create a figure again. All right, there. Okay. So now I've got lots of stuff, but I don't have whole brain activation. So, yeah, looks kind of reasonable. It's always up to you what to do about these things. But yeah, we do want to see, because sometimes what you'll see is like whole brain activity, whole brain deactivation, and then if you just threshold it and show these tiny little peaks, you're just missing the fact that you have massive artifacts or something in your image, you know, that you should be suspicious of, right? So it should be some kind of balance. Ideally, you wouldn't see anything in the ventricles, especially not at a stringent threshold, but there'll always be some, you know, some artifacts. Yeah, we can do 0.05 uncorrected. And try this again. So montage. Okay, oops, there. So that's 0.5 uncorrected. I don't see any huge problems, you know. So yeah. Okay, so that's an idea about that. So we did that, and now let's do the table of results. So now we're going to have to, or want to convert to another type of object, and that's a region object. So now what I've done is I've taken that T-map and I've converted it into a region object. And the region object is convenient for blobs. I mean, I sort of designed it like, you know, 10 years ago as a way of looking at contiguous blobs, right, and doing stuff like you want to extract data from contiguous blobs or whatever, or even parcels, right? Like you have an atlas with 500 regions in it, right? In the region object, it's going to be a series of a 500 vector of 500 elements, one per region that you care about, whether it's contiguous or atlas region or whatever. And then in that is a structure that has a lot of information, like where are the voxels, how do we map them back into the world space, data that you might have extracted and attached, and so on. So for our purposes now, that region object, we're just going to use that to print a table. And now what it's going to do is it's actually going to load that combined atlas that I showed you before. With the 500 regions, with all the different named regions that I put in there. And it's going to use that to automatically label the regions, which I'm very excited about, because I've been wanting for a long time, like it's an easy way. You have activity, it's somewhere in the caudate, it's somewhere in the basal ganglia. Did you just say basal ganglia? No, because we know that there are these different, you know, cortical striatal loops. Right? So one of the components of this atlas, this combined atlas, is the Pauli 2016 atlas, which was a paper that Wolfgang and I and several other people published in PNAS and TAL, maybe? TAL? Yes, TAL. In PNAS, and it has these different loops. So it's got a neurosynth data-driven breakdown of the different basal ganglia parcels. Long story short, I like that one better than some of the other basal ganglia parcellations based on resting state. because it gives really nice bilateral clusters that seem to make a lot of sense and have different sort of associations and different task profiles. Okay, long way of saying that's part of the atlas. So you have this blob somewhere in the basal ganglia, and you want to go, well, where is that? Which corticostriatal loop is it part of? And that means really different things in different studies, right? So it's in there, and it will try to match it up and label it. So you see a lot of stuff in this table. So that's what it's done. When you say table, it loads that atlas, it matches them all up, it adds that stuff to the table, it prints it out, right? Again, very modular, so you could go back and use a different atlas if you want to. You know, there's an auto label regions thing where you can put in any atlas you want to and get out a table and make your own thing, right, based on whatever atlas you want. But this is the sort of default option. And so what it shows you is for every region, you know, what's the volume in cubic millimeters, what are the coordinates, the center coordinates for that region, what's the maximum z value, positive or negative. This is a sort of higher level grouping, you know, so it'll match them with these individual labels. Sometimes they're pretty detailed. Like I actually don't know where 7b is in the cerebellum. Sorry, I don't know. I'm just not that good with the cerebellum. But I do know that it's in the cerebellum. I know that these are in the basal ganglia. And then I also don't really know where 23D right is. But I do know that it best matches the default mode A network. And this is from the 17 Thomas Yo and Randy Buckner 17 network atlas divided by left and right. So it'll match it up with that. There's lots more to say, potentially, if you really think about it. It's actually not that easy to match a blob up with an atlas label automatically, because you have to think about some blobs are really huge and they're going to cover a whole bunch of different regions. Some blobs are going to cover, you know, some percentage of a whole bunch of different regions, right? A lot of them will. So, and some blobs are going to be within a large region, but they'll be tiny and they'll be only a small portion of that region. So long story short, some of these things here that you're seeing give you these breakdowns of percentages of the blob that is, or the percentage of the reference atlas region that's named that's covered. Like, is it all of the region or some of it, or what percentage of it? And then what percentage of the blob is in that region, both directions. So stuff like that. And then if there's multiple regions with some arbitrary cutoff where it's not really meaningful to label it as one thing, it'll say multiple regions. All that work in progress, you can change that. And some of these things you just don't have a label for because they're somewhere wacky outside the brain. And I think my T-map might be quite liberal right now, right? Because I've that's what I've done. So yeah. So if I can re-threshold it here, right, with my FDR K10. I can regenerate that table. I'm going to do something else right now, which is a little off the walkthrough script, but just to show you this, which I really like. It's in some of the later walkthroughs. I'm going to label that table, print the table out, and then what I'm returning is those regions again, but it's separated the sort of positive going and negative going ones. So I've just called CL pos. I've created that as output, and it's got the labels attached to it. So it's got the best label, and it's got whatever, all of the things. So then what I can do is do another kind of montage. Again, I'm going a little bit off the script here, but let's see. Let's do montage CL pos. Oh, I don't know. Say the first 10 of those regions. Let's add some other options. There's tons of options, but I can add this. This option, region centers, says plot just a slice with the centered on that blob. So then you have the table, right? And then you can actually see where each of those things in your table is, and then interpret it. Like this one is not looking so super awesome here. It is kind of close to the cerebellum here. There's 7B somewhere in here. This is most of the activation because I haven't separated it out. So there's actually one blob that covers a lot of different regions. At a higher threshold, that might separate out or would separate out. This is outside the brain, so et cetera. So those blobs, yeah. So that's just a little extra thing you can do. What else? That's it. Table of results. More help, which I already showed you this. So like if I do, okay, help region.table, it'll show me what are the options for that, the creating the table, for example. What are the outputs? How do they work? And then the last thing I should say is there's a whole huge legend that's printed out with the table. It explains what the different columns are. And then also the references. So here are the references for the atlases that I put together. All of them will not be relevant for any given area. But I'm trying to move towards making sure that we have like, you know, the right kind of attribution and make sure that when you see this thing, you know what you're seeing. So that's a work in progress, but I think that that's a direction that I'm heading in, right? So it kind of tells you how to interpret what you're seeing. Yeah?
So I just want to make sure I get this clear. So region is a function that's written into one of the Atlas scripts that you're calling out. So like if I were to, right, would I need to have this region for like all these atlases in the same folder where I'm working for it to be, for me to be able to use this region function?
Almost. Actually, let me answer your question by taking this as a segue to explaining a little bit more about the objects. Because region is a type of object. And so it's one of the things you can do something with. And so long story short, you can interact with regions from anywhere. I mean, it's one of the basic sort of like tools. But for those atlases, you just need to make sure that those atlases are on your Matlab path, or whatever atlas you're loading into an atlas object. So let me back up and go over this. So what I showed you now is, oh, we're almost done. Wait, one more thing. I'm gonna is writing the T-map to disk. So what you do with the this is just an example, a statistic image object. You define what the path name is that you want to write. There's an attribute for that, the full path, and say whatever you want to call it. And then use write. So that's it. Now I've written a nifty image of my thresholded map to disk. So in case you wanted to visualize it in some other program or whatever, right? MRI Crow or something like that, or whatever, or save it, or whatever. Right. Okay, and then we can reload it. So that's that. And what I've hopefully done is just give you, okay, this is probably one of the simplest analyses you could do, but in 6 lines of code, you can go from, you know, nothing to the whole analysis, figures, tables. So that's nice, and that's a short script. Let me go back then and talk more about the objects. Yes? Yeah. So that's this. So that's 30 images, right? That's here. Emotion reg versus look neg contrast images. There's 30 of them, one per subject, and then each image is the average activity when they are looking at nasty pictures and regulating them by generating positive frame versus looking at nasty pictures and just responding naturally. I got that, yes. So we did the whole pipeline through, through SPM in this case, right? Now that could be through anything you want, actually. You could run a different pipeline. You could run FSL pipeline, or whatever. You could run fMRI prep, right? So basically you'd run the pre-proc pipeline that would be like take the raw data, right, which I'm not showing you here, run fMRI prep, let's say, and then take the output from that. Now you're going to combine that with your event onsets. Now you have a first level model, right, where you have the activation amplitude image for look neg and the amplitude image for regulate reappraise neg. Compare those two, take that contrast image. That's what you're seeing here, right? So for 30 subjects. Does that help? Yes, great. Right. Yeah, it's nice to know what you're looking at, but what it shows you at the end of the day, right, is that, yeah, you know what, you really activate the pre-SMA and the dorsomedial PFC and other areas when you engage in that reappraisal process. And we've learned some new things that aren't really widely reported in papers. So, for example, which of the networks are really most important? Well, on the blobs here at least. Oh, those are negative. Okay. Default mode A shows up a lot. Attention, frontoparietal. So those are some of the networks that are the most important. Let's see. And if I do methods, oh, I have to go back. Let me stop doing that. All right, let me go back to talk about the objects. Okay, self-censor. All right. Okay. So let's go back to wherever my website was. Aha. Okay. All right. So let's go to, let's see. Objects. So here are the ones that you really want to use. There's a couple more in the repository. They're either things that you shouldn't really need to call directly because they're superclasses of these, or some of them are a couple are kind of in development. And just so you know, so here's the 5 different types of objects. And I'll kind of give you an idea about what each of them does, and then how you get help on them and look at them. So let's see. First of all, if you actually go to the GitHub repository, like where are these things, like how do objects work in Matlab, and I'll even go back and explain what objects are in this case anyway in a second, but where they are in the CanLab core repository here is all the things with the @ sign are object definitions. And every object then has these methods that go with it. And so these are things you can do with that object. And so basically, like, if you look at the fMRI data object here, these are all things you can do specifically with fMRI data. It can do any of those things, and then any of the things that you can do with its superclass image vector. So all those, each one of those things defines a method. So the idea is, like, the object is this kind of container for information, right? So the fMRI data object here, it's a container for a neuroimaging data set. And then it can store any number of images that you can hold in memory, basically. Then you can operate on those images using its methods. So if you say mean, create the mean parentheses this fMRI data object with data attached to it, right? It'll create a mean image. Right? So it won't do the normal Matlab mean. It'll first look and say, is there an object method in that @ folder that's called mean? And if so, I have this object run that instead. And so that's what lets you run things with really simple commands, for better or worse, right? Because you might say, well, it's kind of nasty to have a command called plot when Matlab already has a command called plot, right? That's bad, but it's good because it's more intuitive and readable, basically, right? So any of these things might have a plot method, and it says, yeah, if you're working with this kind of data, which is this data class, like fMRI data, then you should go and do the special thing, right, instead of the generic thing. So there's pros and cons, but on balance, I'm strongly in favor, actually, of that as an organizational scheme because of the simplicity, I think. Anyway, got more to say about that, but But that's, yeah, I think so. Okay, so that's the fMRI data. The statistic image object, you can have multiple statistic maps. They could be T-maps, or which is mostly what they are for me, or they can be anything you want, really, you know. That has some additions where it'll also store and calculate and store p-values and a vector for which voxels are significant and which ones aren't. So when you threshold it, you're not erasing the data, right? In the image, the object has all the data. You threshold it, and you're just flagging which voxels you want to be significant for display. So you can go back and re-threshold it and stuff like that. So there. Okay, the atlas object. This is an object that's specialized for handling these particular kinds of data sets, right? That are like fMRI data really can be any kind of data. It could actually be pet data too, unfortunately, right? Or SPECT data or whatever. You know, it's just sort of a pretty generic image, you know, container. But the atlas enforces some rules. And it says, hey, I've got some space for probability maps for every one of number of parcels. Like say you have 100 regions in your atlas, and it's a probabilistic atlas. So it's got 100 probability maps in there. And it's got then a data vector, which is which parcel does each thing belong to, you know? So you can like re-threshold based on the probability maps and stuff like that. You can do lots of stuff with it. I'll show you in a second. You can, it's got specialized methods then for, like say you want to select an atlas region by name. I'll show you that in a sec, right? You can pull out the atlas regions by name, extract data from ROIs, stuff like that. So it's got specialized commands, right? But it's, you know. The region object we just talked about, so that stores things in one element per parcel or region, which is often defined as a contiguous region of voxels or as something with a unique label in an atlas. Like, you know, pregenual singulate left or whatever. All right, and then the last thing is this fMRI display thing. And this is probably the one that you may interact with the least directly. But when you create all those slice montages or surfaces or something like that, then it creates an instance of this. And that has a registry for which slices and surfaces do I have displayed in various windows, you know, or in the same figure window. And then it's got handles to all those things so that when you add blobs, you can add them to all of the montages that you have and all the surfaces, or just some of them, or whatever, right? And you can remove them and stuff like that. And so its methods are things like montage creates a new montage, add blobs puts those colors on the brain, right? With various options for color maps and so forth, stuff like that. So that's a little bit about the basic types of objects. Okay, I'll keep going, but questions? Okay, sort of clear? All right, so then some other stuff that we can do. Let's actually go through this atlas thing. Let's see. Oh yeah, the other thing I wanted to say about objects. Okay, so if you want to get help on those things, then what do you do? So you can type methods fMRI data, for example. That gives you a list of stuff you can do with that fMRI data object. There's lots of different stuff, like extract gray white CSF. That'll give you the mean values in each of those tissue compartments for that image. Extracting region data, lots of stuff. But if you type doc fMRI data, nope, not that. fMRI ADA is nothing. Okay, that's slow. Okay, so then it gives you this help file. And it gives you some philosophy, and actually I'm going to go through this with you because I can tell you why, it's more about what these things do. it shows you how to construct a new instance of that object, like fMRI dataset. So you can put in stuff like, here's the image names I want to put in, here's a mask that I want to extract data only within this mask, etc. Oh, it also handles, some of these annoying things for me is you have an atlas or some image that you've downloaded or used on the web, and it's in a different space. So the voxel sizes are different, the coordinates, it's still a kind of an MNI space, but you can't match up the voxels one-to-one, right? So it handles that. So it's got methods for resampling the space of images. So I say, I want to take this atlas, I want to resample it to this 2x2x2 mask, or I want to resample it to my data space, or I want to take the data and resample it to the mask space and upsample it, you know, etc. So that you end up with these lists of voxels that match up. Right? So and that's one of those things for many data scientists who might have super awesome methods, but they don't want to go and figure out how XYZ coordinates match up across different atlases. Is this a problem that anybody else has had, or is it just me? I don't know. Yes, some of you have had this problem, right? Okay, so it handles that stuff. That's the idea, right? You can map things into space, you can check the space, make sure it's the same, that kind of stuff. Right, okay, so this is more about creating the instance, but we've just gone through the basic example of that. And what I really wanted to go down and show you is some things in this help document. I'll show you a little bit about the properties and methods. So in general, properties are data fields that are associated with the object. Like, there's a property in this object, fMRI data, that actually stores the data. Another property that stores the space. Where are you in the brain space for every voxel? Image dimensions, stuff like that, right? Lots of stuff like that you need to keep track of. So those are the properties. And then methods or stuff you can do. And then here's a partial list of some of the methods that you can apply, and then we'll see a full list below. But what I've done here is look at some of the key properties, right, and then the key methods. So here are some of the properties of the fMRI data object. So there's a dat field, and by the way, you can see it if I just go back to Matlab for a second, right here. What's my data object called? I forgot now. It's called something like data object or image object, I don't know. Here. Whose will tell me all the fMRI data objects. There, data object is an fMRI data object. Okay, here's all of its properties. And then you access those with dat. So the actual data is stored in data object.dat always. And data object.dat is a list of voxels by images. And that's actually kind of nice, and it's a single format, so it's more compact. And it's not all the set of voxels. It omits all the stuff that's around the edge of the brain, and if you mask it out in the ventricles and the stuff you really don't care about. So that instead of storing every value in the image, it stores it in a much more compact way, you know. And sometimes, anyway, this can be like way smaller to store a whole data set than all the nifty image files, because they're storing mostly empty space. And yes, you can compress them, whatever. Okay, so that's the data field, and that's how you access them with a .dat. Okay, oh, I'm back in my, where's my doc? I want doc. Here it is. Okay, so that's the image data. This is the record of the path names, like the actual images I loaded in originally when I created it. This is a history, right? So you can do history of that object, and you can get out a printout of what's happened to it. Of course, having that be right depends on using it as you do go through steps, right? So, and that's a work in progress, but I think at least some of the methods, as you apply a method, will update the history so you can see what was done to it, right? Although they could be more complete. Image names, short names, more useful in some ways. You can, to save space, you can remove images and voxels that are empty, so it will automatically do that to also compress the data set, basically, and then you can expand it again to get a full list of voxels. And then this vol info is a structure with lots of stuff about the mapping to the brain space. So that's what you need to reconstruct it back into a 3D brains and stuff like that. So those are some of the properties. You don't really need to interact with those directly much, unless you want to, right? In fact, the only real one I interact with regularly, unless I'm like developing stuff, is the DAT field. Sometimes you can just manually pull out data from that object, right, if you want to. But you can also do it in the object setting, you know. Like mean, we'll create a mean of all the images and return a new object, a new fMRI data object with just the data field, just the mean, for example. You could do that manually, you know, but then it wouldn't have all the other information about mapping to world space and stuff like that. So I like using the object methods. Here's a partial list of methods. Descriptives, it gives you a printout of some descriptives, including another image object that shows you what the coverage is. You know, like how many of my 30 subjects actually have data values, and what's the range of values, what are the percentiles, stuff like that. This is just to save space. I wouldn't really worry about that too much. You can do things like flip an image left, right. You can display its history. You can write it to disk. Here's data extraction methods. You can apply an atlas, any atlas of your choosing, and that would be an atlas object or something that behaves like one. Right? So you might want to suck it into an atlas object first, and then you know, whatever parcellation you're working with. Make sure you don't have any weird non-integer values and stuff like that. So you can apply the atlas to get the mean data value and the full data set extracted by region. You can apply a mask, and this has options where you can just apply a straight up mask and say mask out stuff that's outside the image. Or you can actually use that to actually apply a linear combination or a pattern from a model that you've already trained to. You can apply a parcellation. That's actually pretty similar to the apply atlas. I think they're a little bit redundant still at this point. You can extract the gray-white CSF values. You can extract ROI averages from any set of regions that you care about extracting from. These are a bunch of things, I'm not going to worry about these right now, about handling the brain space. So there are some methods for, again, compressing and expanding a data set, for mapping one thing on one image data set onto another so that the voxels all line up. There's a bunch of display and visualization things. Some are creating 3D surfaces. Some are putting things on 3D surfaces. Like, I haven't tested this lately since I've been updating. So what happens if I do like m equals mean data object, and I can look at it like this, orth views, that's a full image. Where's my t object? All right, so the t might be thresholded. That might be good. So let's try let's see what happens if I do surface. All right, it might take a little bit. It looks like it's generating a series of brain surfaces and putting my map on there, right? So my thing is not that fast, but it's projecting it out to the surface. All right, so we'll let that go for a second. There's different options there. So that's one example of the surface. There's slices. The montage thing is like some of the simplest like point of entry for generating the whole thing. So that's good. We could try this one. And there's some data processing and analysis tools. Interestingly, I didn't put predict in there. That would be the main one that we're going to go through, which is like a stratified, cross-validated multivariate prediction of an outcome using the image data. So like if you want to take all these images and say, how does this predict? So we'll get to that in a sec. Okay, so that's a little bit about these objects and how to get help and examples. So that doc is really helpful. And it also has then a list of all the properties after that and all of the methods. So that was my selected list, but here's everything, right, that you could do right now. And some of them are pretty low-level things, and some of them are pretty high-level things. Like Phil Kragel just added this method. We have to probably rename it. I think that's test generalizability. But that does, is that? Anyway, one of the methods in there does, it'll show you like it'll do a searchlight analysis and say, what's the most predictive area in the brain out of one area? What's the most predictive network? Do you need more of the brain? Do you need multiple networks or the whole brain? And it shows you curves of predictive accuracy, stuff like that, right? So like more complicated things. I think that's the test generalizability. Yeah. Here's another one that I like. Let's see if this is going to work. Let's see. We're still sort of slowly applying that. So, okay, so we got the surface rendered. Yeah, and you can change the color options and stuff too, and do cutaways and stuff like that. But let's try this one. Okay, so now what's it doing? This is another way of doing the whole analysis. So number one, we first did a voxel-wise t-test, right? Voxel by voxel, it's the sort of standard thing to do. Often with a small data set, like 30 is actually a fairly small data set, and especially if you're going to apply a high sort of stringent multiple comparisons corrections threshold, you just don't have the power to really see most of what's going on. In fact, with 30 subjects and a moderate effect size of 0.5, power, if you're going to do family-wise error rate correction, for an average kind of data set in our analyses is 2%. Like you'll see 2% of the stuff that's really there, right, with family-wise error rate correction. So that's not that satisfying. In fact, it's pretty much a losing game. So some people will say, oh, well, every study should have 100 subjects, or maybe that'll be 1,000 subjects one day, or 10,000. There's really no end. But the problem is that you can't ask interesting questions, usually. I mean, you can ask some interesting questions, but there's an awful lot of questions, new tasks, new whatevers, that you just can't ask in a giant data set where you put all the eggs in a 1,000 or 100,000 person data set. So I think these small studies are really important because we need to explore the space. People need to design tasks and try new things out, Okay, that's a point of philosophy, right? I think that the MID task, monetary incentive delay task, is great. I do not think it's going to explain drug addiction, So I don't think that that's going to be like the one thing that people should use. So we need creativity. Now, here's the tension. Okay, you want to do a new study of this thing that you designed really carefully, or this small population like the infants, infants in pain. We're working with one of the data sets from Oxford, babies in pain. Super hard to get. You can't do 1,000 infants in pain. But, and you can't correct for multiple comparisons reasonably across the whole brain. So what do? You break it up into larger chunks. One set of useful larger chunks is these networks, 17 networks, right? Separated left and right. So there's actually 16 unique networks with actual voxels in them in the Thomas's data set, apparently. So there's 16 left, 16 right, that's 32 regions. Now, so I can average across the regions. So when I run this method on my data set, it does the t-test, but what it does first is it applies that atlas, right? The 17 network atlas left and right. So those are my units of analysis. And now what it's showing me is the networks, and it's showing me whether the mean, the t, the p-values, and the significance level for the right-sided activation in control network A, B, C, etc., the left-sided activation, and then I got inspired to do this actually because I wanted to start doing a fair test of lateralization, which is kind of complicated sometimes to do. So if you can assume that you have a left part and a right part where the things match up anatomically in some meaningful way, it can't be like, but they're actually left and right, then you can test whether there's significant lateralization left or right. So I wanted a good way of doing that. 16 network seems like a pretty good chunk to try that on. Every one has a left and right component, so it gives you a test of lateralization. So this is another way of looking at the data, right? And that's what's done in that method. So it's just an alternative t-test. And what you can see from that, and actually what this one does, is prints out a table and a summary and a little report. And by the way, some of these are Bonferroni corrected there, the 4 stars. So then it will print out this report, and it will say, aha, well, with Bonferroni correction, I don't have any networks with bilateral increases, but I've got right hemisphere control B and default B network increases. And I've got right lateralized activation in control A, default B, and default C. No left lateralized activation. Okay. So that gives me an analysis of the lateralization. And it also shows me a plot. Where did that go? Here. The names are kind of hard to see, so we got to sort of work on those a little bit. But this is a plot where the farther out it is, we call it a wedge plot. The farther out it is, then the more activity there is. This is the mean, and then there's the error bars in dark red. Red means activated, blue means deactivated. So I can see, and they're grouped by left and right hemisphere for each of those different networks. So each color is a different network, left, right, left, right, left, right. All right, so with a little relabeling of these regions, this could be a useful plot where you can see this is default B, left, right, right? This is control B, left, right, and so forth. So you can see where there's activation and where there's not, and then the stats tell you whether there's significant differences left and right. Okay, so I just wanted to show you this as two things. One, alternative way of doing the simple test, right? And B, that using these tools, like I don't think there's an easy way to do this in other packages that I know of. Is there? I mean, I don't know. Maybe, maybe not. But the nice thing is, like, you know, you have this sort of block set, and then you can do this thing which tries to tell you the information you really need, right? And if it's highly reusable, it can make it a method, you know. So this is a set of things that you might really want to know about lots of data sets. And then what it's created from is these other similar methods. So the script that does this, well, it's pretty simple. Maybe I won't look at it. Maybe I will look at it. I don't know. But basically, the tools that uses, the lower level blocks it uses are things like, there's one called Wedge plot by atlas. What does that do? Well, it applies the atlas to the data set, extracts the wedge, you know, plot, right? If you have multiple images or replicates, it'll make the error bars, you know, stuff like that. And then there's the table, right? So it uses those basic pieces to do that. And then this is a montage. So you could do this with one line of code too. So the code, you know, that does, so you could create a different test or a similar test like this, right, that you want to do by either dropping in a different atlas or, you know, with a sort of moderate, minimal amount of coding, really, right, using those lower level blocks. Okay, so that's more on the objects in the philosophy. Oh yeah, let me go over one more thing here. These are all analysis methods. So maybe we can go to an actual sort of predictive analysis. I kind of promised that. So this predict method does that. And we can explore that one soon. There's some quality control metrics. There's lots of stuff. Okay. And that's how you get help for the objects. All right. Let me pause there. And how are we doing on time? Am I finishing at 12? Okay. Wow. 15 minutes. It's crazy. All right. Let's see. So we did that. Oh yeah, here I'll show you this quickly, and then we'll do a prediction one. Okay. And then that'll be it. All right. So here's my atlas. This is one of a number of atlases I could have loaded. You can do this along with me if you wanted to. So if you do help load atlas, if you remember that, it shows us the different atlases we can load. Right, like any of these, but you can also put in your own. Okay, or construct one. It's pretty easy to suck an image from the web into an atlas object. It's just one line to say atlas object out of this image with integer parcellations. And then we can visualize it. We just did that. We looked at them, just did it again. Now let's say we want to select a subset of regions. Let's say we want to do an ROI analysis. right, on my atlas in the thalamus, because I like the thalamus a lot. So what this is going to do, let me make sure that I've loaded it first. Okay, I've loaded it. So now atlas object contains that. Now I'm going to, there. I'm going to pull out all of the regions that have thal in the label, right? So if you look at this first, this atlas object, one of the things it has is labels, multiple labels potentially, right, and descriptions. So this has 489 labels for 489 regions. That's my combined atlas. But now I've pulled out all the thalamus ones. And so now I can look at the thal.labels. I've got the pulvinar, lateral geniculate, medial geniculate, ventral posterior lateral, et cetera, right? So these are some high-level groupings. Okay. So now I can do that. I can also just select a certain subset. Let me see if I have this loaded in already. I had a pain data set. Oh, I replaced it. Oh well. But because the pain should activate particular parts of the thalamus, like the ventrolateral thalamus, medial dorsal thalamus, not LGN and MGN, the habenula. So we should see different activity with pain in different parts of the thalamus. Now we're looking at the emotion regulation data set. But that's fine. We can get the whole thalamus by just flattening and just saying I want one region with all the thalamus regions mushed together. So you can do that. But this method, select atlas subset, lets you pull out things by number or by name from the atlas. So that's an example of one of the kinds of functionality that's helpful. And then, I've got this data object. So now I can just extract the ROI averages from all of those regions. Each one of the regions. So now, right, what I've done is I've got 30 subjects, right, 30 images, and I just want to test like a particular part of the thalamus, right? But I've got 7 different parts of the thalamus. So now I've extracted the data set from all those regions. They're in a region object, which I've called R, creatively, right? So I can do stuff with that. But for now, I'm just going to pull out the data. And now I've got the actual averages where each column is a region and each row is a subject. So those are my averages. Now I can do the Ttest or group analysis within that, within those regions. Oops. Oh no. Maybe I misordered my things. Oh yeah, I think my labels were. I have to go through and run it. Let's try this again. Let me see here. So now I should have the 7. I have too many labels. Okay. So there. Now I'm going to extract because I was doing these things out of order. So I should have the same number of regions. Okay, now it should work. I hope. Yay. Okay, so there. So now this is a series of ROI analyses, right? If I want to say that different parts of the thalamus are active, it turns out in emotion regulation, none of them are really active. But if we had loaded the pain data set, then we would see activation in meaningful parts of the thalamus. So that's an example of how to do a region of interest analysis, and a little bit more about using the atlases. So that's part of the basic tool set. Let's see. Yeah. Okay. Here, I'm going to go to this last one now, I think, since we're very quick. And we actually can go back to the thalamus regions once we have the pain data set loaded. So this is going to be, here's my walkthrough. Okay, here. So this is the URL for that. It's Hackathon Predict Example 2018. I thought about putting this on Figshare, but I think I probably will. So it'll be more stable later. But for now, you can get it there. That's a pretty small data set-ish. It's a few hundred megs. And what it's, so I'll walk you through this. And okay, so this is about this data set. It's 33 people, and what I like about this data set is you can do a lot of other stuff with it. There's 6 different levels of heat pain, painful heat, or from non-painful to painful, within each person. So there's 6 images per person, right, with increasing levels of heat. 44 degrees, 45, 46, 47, 48, 49. And then there's a meaningful relationship with pain. So for every one of those, every image is an average over some number of trials. I think it's like 8 or maybe 4 at 49 degrees. So a few trials, right? So the image is an average over a few trials of painful stimulation at that temperature. And then accompanying that, there's an average pain rating that goes along with it. And so that's what about the data set. We can create contrasts, like linear contrast across the intensity levels, and test that, and do other stuff too. So let me start running this, and the first thing that we'll do is we'll just look at the ratings, and you can see the ratings go up across temperatures. This is the group average. I'm just going to run this stuff because we're kind of short on time. But all we're doing right here is because I've got 6 levels per subject. I'm just concatenating them, and I'm creating a data object, which I've called brain data temp averages for some reason, that has all the images in it. And it's also attaching 2 kinds of data. So one of the attributes of data is .y field. That would be like for outcomes that you want to predict, let's say, or in this case, pain ratings, right, that people made. So for every image, 6 images per person, and there's going to be an image, and there's going to be an average pain rated for that image in the outcome field, right? And then I'm also attaching the subject ID, and that's going to be useful for cross-validation. And probably actually Gail's going to go over more of that stuff later, so maybe this is actually not so bad if I kind of go over it briefly. So it's showing me the data set again, just to see. So we looked at that. Okay, so now we have the data set in here. So that's what it is. And I'm about to do a prediction then, a multivariate prediction of the outcomes, where I take the images, I'm trying to find a pattern across the images that best predicts the increase in pain within and across subjects. I might take a really quick step to the side here for 1 second and go back to my thalamus thing, because I'm kind of curious. So if I just redefine this data object and use the pain data set, right? So there's actually 198 images. I'm just going to ignore the fact that there's different intensities for right now, for time purposes. But now I'm going to make it extract ROI data from the thalamus for each one of those, for the pain data. And we'll see what that looks like. So there's this table of statistics and stuff too. So what do we see here? It looks like, oh, this is going to be there's a lot of data points on here, but the visual thalamus is deactivated. The auditory thalamus is not activated, but the pain-related thalamus, intralaminar nuclei, ventrolateral complex especially, mediodorsal thalamus, all activated. Okay, that's kind of quick and dirty. And you can see the individual spread across the individual images here. But, so this is not quite correct because there's multiple intensities per person and all that stuff. So I could have picked out the high pain ones, but whatever. Okay, so you get the idea. So I did the ROI analysis in the thalamus. That works out pretty well. Okay, so now we'll just go through the last bit, which is going to be this cross-validated prediction. And sorry, I guess I'm not walking through a lot of the details of this, but this is a sort of standard prediction thing that we have been working with. Oh yeah. So right now, what have I done? I'm running the predict method. That's methods for fMRI data. So you can run it with any fMRI data object. You have to first attach that outcome value field, which is .y, which is the pain ratings in this case. So 1 per image. And then what it's doing, and then I'm also telling it which subjects belong together. So I've got 6 images per subject. So this subject ID is a vector where all of this subject number 1 gets a value of 1, subject number 2 gets a value of 2, etc. So it's just 1 to 33. And what that's doing is I'm passing that in, and it's then holding out all those images together. So it's training on 32 subjects, testing on all the images for the left out subject. So that would be a leave one subject out cross-validation, where I've left out all the images from that subject. You could do other things, like if I had a little bit more time to comment this and work on it, for you, which I will do, I would do like 5-fold. So I'd leave out all the images from 20% of the subjects. And it would run a lot faster too. There's some advantages to that. But this will work for our purposes. And I just put in my algorithm name I'm going to run is this cross-validated lasso PCR, which is principal components, decomposition, penalized regression, with or without penalties. Here we're not using much of a penalty at all, so I don't need to go into the details of that really. But it's it's a still standard algorithm. We could use support vector regression. We could use Matlab's version of the lasso or ElasticNet or whatever. Anything you pretty much want to plug in. You could add pretty easily. And then we'll pass that into the predict, and it's going to give us an answer with the cross-validated regression. And I've got it. And now, oh no, I don't have it. It's actually pretty darn slow. This is actually much slower than usual. But when it's done, I would get this stats output. I think I actually already ran it. I quit. Yeah, I did. I ran it already. Right before this, like 5 minutes before. And so I have that, it ran. And then I can look at this stats output, and it gives me a lot of different fields. It has the actual values. It's got the fitted values, so what's the predicted pain? That's cross-validated. So it's a fair estimate of what the predicted pain is. It's got what the holdout sets are and other stuff. I won't go into the details. It's got the correlation between predicted and outcome, which is 0.56 across all the images. And it's got an object with the weight map. So where are the predictive weights? So I just have a little code block here that shows us the results. And it does it 2 ways. One is the dumb way, which is just lump across all the images. So you can see what the relationship is here. But then, of course, each subject has a different, has 6 data points, right? And each subject has a different slope. So now on the right-hand plot, each line is a subject. So you can see the individual subjects. If they're all going up, if the lines are positive in slope, they're all sort of positive on average. That would be a group level significance test. I can look at the average correlation within person. I can break down the variance by within and between person, etc. But this kind of gives us a plot of how well it's working. And to do that, I use one of our toolbox functions. It's called line plot multi-subject, which conveniently plots these things in different random colors in a spectrum, something for the different subjects. So I got that, and then I can also. This is just a little bit of stuff. To just summarize this, I get a continuous readout of what's a predicted pain, and I can do a couple things with that. One is, and the code there is very simple, so I won't keep you from lunch. So you can have it and look at it. Pretty simple code. I can look at, for each comparison, 44 versus 45, what's the accuracy across subjects? Like how many subjects would I get it right if I had to predict, which is more painful. And I can look at the effect size. Co and Z, real simple. So how big is the difference between 44 versus 45 for that individual person divided by the standard deviation? So this table shows you that. And what you see is, if this is actually in kind of the non-painful range, then this pattern is not very accurate. This is probably not different than chance. We could get confidence intervals for that from the binomial distribution. Effect size is nil. But as you go up from 46 and to 47, now in the top 3 range, you end up with pretty high accuracy rates, or even here, I guess, and pretty large effect sizes, right? Somewhere in the range, in this data set of, well, 0.75 to 1. Usually this one's a little low on the top end. There's only 4 trials. So you can get an idea of what the effect sizes are. So the idea is, if it's in the painful range, it's the effect sizes are pretty large. So that's another way to summarize the results of that. Okay, so that was the quick and dirty. We went all the way through the toolbox. We did the objects, what you can do with them, creative construction of stuff, some walkthroughs about the basic analysis, some things about atlases and lateralization, and then we got to a multivariate prediction, sort of standard out of the box one, but in an example data set for that. So that's the whole package. The last thing I want to do, first I want to pause and see if there are questions. I've got one more little bit to tell you about the pain data set, the big pain data set. So any questions or issues? No. We can't leave until there are 10 questions. When's lunch? Yeah. Can I what? Oh. Yeah, that was the Atlas one. Yeah, that's not on the list. I will. I'll comment it more, and I'll make it one of those examples. So I'll push it into the Calendar help examples, and then it'll be up. So I thought that would be. I did the ones that are on there. I thought this would be good to fill it in a little bit. I'm still developing documentation, but yeah, I will. Okay, cool. Last thing that I'll tell you is about this this pain data set. If you're interested, please do get in touch about it. Pain is a $600 billion a year problem, and there's lots of interest right now in developing measures that are predictive of pain, that can help corroborate pain, can help understand what is it in the brain for a given individual person is creating the pain. And that might be different for different people, and it might be different, for healthy people with evoked pain and then different pain conditions. So we've been working a lot in this area, and if you look at our, lab website and papers, you might find that. We just had a paper came out yesterday with a pain signature applied to 600 people from 20 sites across the world, which I'm excited about. And it validates this predictive model I showed you trained this way, just like I showed you just now. On one data set, which is a pretty small data set, actually generalizes to the sites across the world with really large effect sizes. Like for pain versus rest, effect sizes of 2, very large. And you can see it even in this data set here, it discriminates with 1 degree differences pretty well, stuff like that. So it's really worked across different data sets, but we can do a lot better, and there's lots of goals. Goals are things like, can we individualize predictions for each person? Can we just predict better? Especially, can we explain the between person variability better? Can we stratify different groups of individuals so that some individuals have some areas are contributing to pain or predicting pain more than others? That's some of the questions, but there's lots of other questions, but those are some of the big ones, I think, that we're pursuing. This is the data set that I shared with you, which is the larger download, 15 gigs. Each one of these folders is a study. Sorry, it's not too extensively documented right now, but everyone is published. It's a single trial model. Each of these files has one file per subject, and those are the objects I showed you. Those are those fMRI data objects. So you can interact with those. You can load them and interact with them the same way that I showed you, or you can take the data and do whatever else with them. This, for every one, there's a metadata object, which has, for every trial, it has stimulus intensity, pain report, and some metrics of quality for that trial, variance inflation factor for that trial. And there might be others too that are mix and match across data sets. I don't have a lot of person level data in there, like is this person anxious or whatever, you know? It's mostly this within person thing. Yeah, so if you're interested in that, you know, happy to talk more, or you can give it a shot and try something. We're using this data set and extended with some other studies as well to develop new models. So our original models were developed on small samples. Now we've got, you know, hundreds of people to develop models on. So we've got some new things on that. We're working on a stratification project where different people have different bases for pain. Working on reliability and on, you know, what are the different brain areas and networks that you really need at a minimum to encode pain, you know, and predict it. So that's there for you as well. And I think this is a good time to have lunch then. So I hope it's been useful. Thank you very much.
That data set is now in an S3 bucket you can grab.
Oh, good. Oh, nice. Yeah. Oh, yeah, we can, okay, sure.
Let's get back there. I guess you can watch them over the weekend. We're happy to have Tor Wager here with us.
Hey, thanks everybody. It's great to be here. I think this is going to work now. Or it was on. Let's see, PC maybe. No, HDMI.
Maybe on.
All right. Nope, I think it's my box. Let's see. Aha. It's good for the moment. Anyway, so hi everybody, it's really great to be here. I'm happy to be invited, and good thing I got ready and then let Ariel off the hook, stalling for time. That was getting a little hot there. So I have a sort of very non-traditional plan for me, which is to go through some of our object-oriented tools and actually get you going doing some stuff. This is my plan. So in the spirit of the hackathon, it's sort of roughly filled in, and it is sort of gets a little bit progressively looser, I think, as we go through. So I start by giving you some, that's not working well. It's just not. Yeah, kind of an overview of my philosophy and approach, what I've learned from data analysis over the last 15 years, if anything. Then talk about some of our object-oriented toolboxes for interactive data analysis, philosophy behind that. I'd like to get everybody downloading the toolbox and giving it a try along with me. So that's the plan and the hope. So I have very little in terms of a talk, which is really good because I may or may not have slides at all. You know what, does anybody have a different connector? I think this box is not working well. So if there's another USB-C.
You run into HDMI connection. Chris, can we borrow your...
Yeah, if there's like a, yeah. Yep. All right. A little bit about me. I'm a big fan of Apple until recently. Yeah. You know, this is what they did. I bought this new Mac. Thank you a lot, Chris. Thinking that it was going to be, you know, better because I always get a new Mac. Some people get a new Mac when they like publish a paper or get a grant or something like that. I get a new Mac when my old one breaks and my PowerPoint goes out in the middle of a talk or before a talk. And so I did that. And then my new Mac has only USB-C connectors, I found. So, and then my iPhone has only this one connector. I can't even plug my headphones in anymore without buying a separate adapter. So I think my Apple days may be done after this. Plus, they're valued at $1 trillion now, and I'm just never going to be okay with that, pretty much. That's a problem. New York Times has a terrific graphic way about this. They have these little squishy things bouncing with the volume of the squishy bubble is proportional to the value of the company, and they show you what $1 trillion is worth in terms of other companies, like all the aerospace companies together, etc. It's really interesting. I tweeted it. So it's in my Twitter feed. There's a link. So here's the overview, right? And installing tools. Some basics about object-oriented programming in this system. I've got some simple analysis plans. And they can get progressively more complicated, but the whole idea is to have this tool set that you can use to do all kinds of analyses, and you can plug in your own analyses and predictive models or whatever, and then use the object framework to help display results. So I have an example of a mediation analysis, multivariate prediction. We have a batch system, and I have examples of that I think different groups are starting to use. And then I have a pain data set that I have shared with you. And my goal, I'm always a little bit over-ambitious, I gotta tell you, a little more about me. I liked Apple until recently, and I'm over-optimistic sometimes. And this idea was that I would give you this data set, and if people are interested in it, they could give it a try, download it, do some prediction. Some of the examples that we'll go through are about pain prediction because it turns out to be a really good, strong signal, and it's a really interesting area. And I might go over that in some slides soon, depending on if we have time. But it's to download that pain data set, and then if people wanted to work on it, they could work on prediction, connectivity, whatever. It's about 15 gigabytes of data, and it's single trial models from 7 different studies. So there's about 25,000 images with single trials. And so you can look at connectivity across trials and all kinds of stuff. Well, we'll see. So probably we won't get there. Well, we'll get to the data set. You can actually start downloading it right now. So there's 2 of these URLs there. You know what I should do too is maybe during the coffee break is share the slides or something so that people have the links that they can, click on. All right. Other stuff is shared in the code, so I'll go through it. Let me start by just talking a little bit about my design philosophy and a little bit about interactive code. So I think that, these are all goals. These are goals I've learned to strive for over the years. So what's a perfect analysis look like? It's something that's reproducible. I feel like maybe a lot of this is maybe preaching to the choir, but you're getting 2 weeks of this, but who knows? But I think this is, they're sort of hard-won things for me. So that you or somebody else can rerun the entire analysis. It should be interpretable. This is really hard, I think, that the code should be really simple and easy to read. Anybody should be able to read that code, maybe even if they're not that familiar with the system. So that's a big challenge, right? Because I think we've all had experiences trying to download some other data set or work through an analysis, and nobody's got time to even do their own analyses, much less go through somebody else's code and figure out what they did. And there's a tension. The more creative you get with what you want to do, which is good, then the more complicated things get, which is bad. It would be documented. There would be a code book with explanations of all the variables in the study context. The code would be modular. It would be reusable. So any code you write would be shareable in that way and reusable in that way. There would be positive and negative controls built in. And for a toolbox, a unit test that would, test out all the code and see whether it's working correctly. Yeah, so this is really a difficult thing often, but yeah, I like the idea of positive and negative controls. So something that you should see if the thing is working right, that's positive control, and something that you shouldn't see if it's not working right. And this applies to toolboxes, or it shouldn't see if it's working right. It applies to toolboxes, and it also applies to analyses as well. So when we design neuroimaging studies, we try to build in those things more and more, positive and negative controls for every experiment. There would be a history, so it would track the history of the analyses and results, and the whole thing could be packaged up in a way that somebody else can use. So those are goals. Why should we pursue those goals? I think there's a lot of errors. This is one of the articles from this Nature special section on reproducibility, which many of you may have seen from last year. It just makes the point basically that mistakes in peer-reviewed papers are really common. There's lots of different issues in this whole series of articles that many people have written about. Things about false positives, things about lack of replication and statistical errors. I just like this quote. This is Nick Barnes, director of the Climate Code Foundation, who says, "I'm a professional software engineer. I want to share a trade secret with scientists. Most professional software isn't very good." So I figure I could add some not very good software too. Or hopefully some better software that many people have seen and looked at. And I think that in the spirit of this, probably everybody here is writing code. Who's writing code to do their analyses? Oh yeah, who's not? Just tell. Yeah. Right. So this is getting pretty common. Lots of scientists develop software, write code, spend a substantial proportion of their time. How many people spend at least a fifth of their time writing code or software? At least. How about half their time? How about like 80 to 90%? Yeah. So, I did that too in graduate school. And I still actually do some coding, which is why I'm here talking to you about these tools. And I've learned, I started off wanting to be really creative and sort of do my own thing, right? Make the analyses fit the questions I had. And probably many of you might feel like that. And then I sort of gravitated to more and more wanting to reuse code that exists, to reduce errors, and then even building. Then this is the idea of what, the toolbox that I have here now is. It's this attempt to build something that's really modular, that lets you be creative, but also has very reusable code blocks, and objects that do things. Okay. Right. So errors are really common. I think everybody probably knows this here too, that I really like to share our results because that helps make them useful. So more and more I think about a publication not as the end point, where I learned in graduate school to think about it as the end point, but now I think about it as a starting point for something that I'm building. So that's a really pretty different way of looking at things. Because then I care about the paper and the publication, but I also care about the data set after the publication, and I care about what happens to it, and I care about whether we can reproduce that, whether we can replicate it, whether we can extend it, whether somebody else can do that. And often, not always, but sometimes, we've published papers from the lab. We already have done several other experiments, and so we know that if we're making a claim in the paper, that it actually replicates in several other experiments. That's a goal. That can't always happen. But it's pretty nice if you have a layout of where things are heading, and then you don't end up making claims that end up being wrong later. So I think there's lots of ways of creating value and utility that are beyond publications. But I really, and publications are important. But I sort of started out thinking that was it, and now I think there's a lot more out there. I think this is really important too. How many of you are perfectionists? Well, this is a really homogeneous group of perfectionists who spend 80 to 90% of their time writing code. I was a perfectionist too. Sometimes I am, but I've tried to let go, so I don't beat myself up too much. I think it's really easy to take this sort of high-minded view that every analysis should do all those things that I said and be perfect in every way, And I don't think that it's realistic. I don't think that it's possible. I think they're goals. I'm working toward those goals over a period of years. But yeah, if I tried to make everything perfect, then I wouldn't be here because I would never have published a paper. And I know one or two people in psychology who were actually like that. They're so sort of, they want to do everything so perfectly, or they really want to be right. That's really good value, But then they only publish a couple of papers. So how many people have read Saul Sternberg's paper on separate modifiability, 2001? Darn, because he's like one of those guys, actually. He invented the Sternberg task. How many people have heard of the Sternberg task? Okay, it's a working memory task, and a few of you. It's a very famous task in cognitive psychology from the 70s. And he published that paper. He published this Active Psychologia paper on separate modifiability. It's very deep. It took years. But none of you have read it. It's really sad, So by the time, right? And if you just do that, right? By the time you do that one thing and you wait, you would need 20 years to answer any questions, and then, the field would move on, and people might not hear about it, and so forth. So I really think, in science, that here's what I say: it's got to be right. If it's wrong, like your results are wrong, there's errors, that's bad, you cannot go forward in science. But I spend an awful lot of time trying to be perfect and rerun things, or I could tweak this model this way, I could tweak it that way, and rerunning it, 20, 30 times, trying to get it just right before we ever published anything. And I think that's that's self-defeating. It's actually not that great, for science, And if you even think about the return on investment, right? Then, I could have done a lot more other stuff. By the time I made one thing perfect, which you haven't read either, I could have built a lot more stuff and done a lot more stuff. So I wanted to say that, especially to you all, because I think that might be controversial. I think but that's a value. And so I have these, like the seesaw, right? Sort of competing values. I want everything to be right and perfect and do everything as well as we can. I also want to move through the space and know what's important and what's not so important, in the grand scheme of things. By the way, I think we can discuss any of this, so you can disagree with me or comment if you'd like. JB.
I don't think I disagree. It's more like a culture of papers as fast as possible. What we'd like to have is moving the center of gravity of that culture towards things that are more reusable and people actually study and things like that. So it's not really, I actually don't disagree. I think you're right. It's basically how do we move that kind of culture to be in the direction that we think is more efficient for science in general.
Yeah.
That's a comment.
I agree with you too, yeah. I mean, there's a lot of people out there who are sort of exactly the opposite of you all, they want to hire somebody else to write their code, publish the paper, whatever it says, no matter whether it's right or wrong, and then go on and use that to get more grants and papers.
More the danger.
Well, that's a danger. But I suspect it's less of a danger for you all. So it's just funny, right? Because you don't want all those people are going to keep doing that, right? And then if everybody on the other side is like, you know, the high priests, and then you don't do anything, then you won't be able to have that impact, you know. And I don't know. I spent a lot of time, you know, beating myself up over that too. It's interesting because, like, yeah, I think I learned a lot too, you know, like by rerunning things and reanalyzing things again and again and again. I learned a lot about looking at data and what, you know, neuroimaging data is like in particular. A lot of sensibilities that were really good. You know, it didn't translate into sort of the level of immediate productivity that I would have had. I don't actually really regret that because I think I did okay, you know. It worked out, I think, in the end. And so, you know, everybody gets to define their place, right? There's a place for doing something that's sort of done better than anybody else does it, whatever that thing is, you know, and then that takes a lot of work to do it. So I also don't want to sort of discourage that, right? It's a personal choice. All right. So I realized that I might be the sort of black sheep of this workshop. Picture a black sheep in your mind with the words Matlab written across it. So how many people program in Matlab or use Matlab? You do! I love you. No. How many people use Python? Yeah, both. That's good. How many people use IDL? Oh, too bad. It's out. So yeah, so I figured, you know, Matlab is that's all of these tools are written in Matlab. So if you like Matlab, this is good news. If you hate it, then sorry. I'll learn Python one day soon. I think that, you know, I think there's a lot of value in Python actually. It's got a lot of advantages, especially interfaces with, you know, web applications and being able to deploy in any server really easily and so on. So that's what some of the biggest limitations in Matlab are really centered around that. You know, can you deploy it on a server that can serve things to the web easily or do back-end analyses really easily? Can you deploy it on clusters without paying a lot of money? But I think that, you know, so Python is great. I think Matlab is also great. You know, I think some of the good things are there's a lot of high-level support. So they have really good engineers who are developing stuff all the time. And generally speaking, I actually found some bugs. I found one recently in Matlab, kind of core functioned, I think. But by and large, they're like really good, actually, I think. So, you know, so you have to pay for Matlab unless you want to download Octave, which might work. But then on the other hand, you know, there's a lot of support for that. And I always feel like, you know, if you can pay for something, you should, right? If you value something, money is a way of valuing that thing. So I like free stuff. And I also think that, you know, when we can, I'll pay. And then someday, you know, like all the code I'll show you might be refactored in Python or done something, you know, something might happen. Luke Chang, who was my postdoc a few years ago, took some of the code, some of the core tools I'll show you, and rewrote them in Python. So that exists. But I've kept developing the Matlab thing. Okay, so this is not a real talk, as you can see. But it's really just an introduction to trying to try these things out. And this is pretty new. I haven't done this kind of workshop before, so bear with me. Things will probably go terribly wrong. But we'll see. So this is the website, canlab.github.io. Everybody's familiar with GitHub, I'm pretty sure. Yes? Good. There. So this is the idea. So I'm going to go through this. And I'd like us to download the the toolbox and to start trying stuff out. And I've got a series of demos, and the goal is to get you to a place where you know what these things are about and you can use them, and maybe even extend them later. That would be awesome. So here's the idea. I'll just walk you through the philosophy there. So the idea is it's a set of linked GitHub repositories. There's, see in a second. And the idea really is that we have lots of good tools for pipelines. So there are standard pipelines that exist you can run things through. But the whole idea of a pipeline is interesting, right? It's like you take whatever big data set, and it goes chug, 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 and you get an answer, right? So it actually, minimizes interaction, increases standardization, and it's a big black box at the end of the day. I think most of the neuroimaging analysis software out there has kind of been designed with that in mind, and there's a lot of work on those things, and you've been working with some of them, I think. The idea of bids and fMRI prep and other things like that. Some tools are like very flexible pipelines, like Satra's tools. But what's I think was missing for me in all of this, especially as I started working with SPM, which is what I learned to do early on, is really this way of interacting with the data. So SPM sort of gives you output, and FSL gives you output, and it gives you reports. But it doesn't let you really dig in, So my first experiment when I was in graduate school was this was an fMRI study. I sort of got permission to run the study and did that, collected my first subjects of data, and then my advisor, Ed Smith, was like, okay, well, we'll see results in a couple weeks, right? And I'm like, sure. Couple weeks, okay, I want to do this. And then, I said, well, what do I do with the data? They said, well, talk to Doug Knoll. And Doug Knoll said, oh, well, you have to reconstruct the data first. Here, you can edit my script in VI, my recon script in VI, and then reconstruct the data, and then analyze it. And I said, what's VI? Because I didn't know. It's a text editor. How many people use VI? Yeah. So there you go. So I learned about that. But it was really starting from scratch. And then I got my first results, and lo and behold, there was just nothing happening in the brain. And that's like the worst thing, because then you go, oh, well, now what do I do, right? You have to go back. And especially at the time, in the software packages of the time, like SPM and Boxbow, there was no way to look back and actually look at the data. And so I just wanted to say, what's the, impulse response function look like in the visual cortex? What's happening? And nothing, right? You just can't do it. It shows you the glass brain, and then you have to start writing and digging in, writing a lot of custom stuff. What was always missing for me was this sort of balance of being creative and being able to build with like a sort of a tool set. Another thing that was missing for me was I saw over the years many people who were very talented analysts and statisticians. So some more advanced statistical models that are really fancy, more, different kinds of machine learning models now, and they couldn't really be plugged in, to neuroimaging data. So what would happen is someone would develop this really great model, and everybody would keep using SPM and FSL, which is like the same, and those are great, okay, and they've also developed, and they have lots of great tools and all that stuff. So I'm not saying that they're bad. I'm just saying that the basic bread and butter, kind of analyses that people do, there's potentially things that you could do that are a lot better, a lot different. There's people out there who are not imaging experts, who are not going to sort of hack around and write a whole bunch of code, to try to visualize imaging data, but they have really good models. And so I wanted something that's really extensible, that you can take as a framework and plug in any model that you want easily. And then you can use those things to visualize, you can use the tools to visualize the data and to do image operations, and so on. I think, by the way, that the idea of NiLearn is similar to this. I think you went over that already, did you? Did you guys do something on NiLearn?
We might see it on Monday.
Oh, right, okay. So I think what Gael is doing is, I think is very much aligned. If I think there's another example out there, that would be it. So like scikit-learn and NiLearn, right? Which has a very, I think, similar kind of philosophy. But it hasn't, I don't think it's really been there, you know. So we want this thing to be, toolbox to be interactive so that you can work with objects with really simple commands. We want it to be transparent. That if you write a script to do something like generate a montage of slices with colors or surface rendering, or reconstruct things, you know, from some other representation into a volume, you know, brain volume data or whatever, they should be really simple commands. And so that's what I like about the object-oriented framework, is that the commands can be simple, like plot, you know, or montage, or surface, or whatever. And I think that reduces the coding errors too, because a lot of the hard work is done under the hood, and if the function works right, if the object works right, it just does what it does, and it does it right, hopefully. Right? And then you can interact with it really easily. So pretty much, you know, many people can write and the scripts and read the scripts that are written. A big problem I've had, I've been writing code for 15 years, I guess, related to neuroimaging. Since my first null results, and I had to go back and try to figure out how to look at the visual cortex, you know. Yeah, I just started writing toolboxes then. I've gotten a little bit better. I wasn't trained as a software developer by any means, but I've learned some things the hard way over the years. So I think we've gotten somewhat better. One of the issues is discoverability. You know, so how do you find out what's there? You know, so that's been one of the big, I think, challenges. So we have a few objects. I can go through what they are. And there's only like 5 objects, really, I think, basically, that you would ever use. And then you can type, you know, methods for any of those objects, and you can see all the stuff that they do. So that helps with discoverability. Simple commands help make things more reproducible, and they help minimize errors. I'll also, I think, you can get there, attempt to show you this this batch system. Oh, what happened? Oh, what's it doing? Oh, it went back to the slides, huh? Interesting. This was happening before, right? I mean, you were seeing this stuff? No, you were not seeing that. Oh, I see. That's so interesting. Here. Here's my principles. That's on the main page there. Yeah. Whoops, that's not it either. It's so complicated, this stuff. Okay, there. I want a mirror. Hang on a second. Let me see if I can have us seeing the same thing. Maybe that would help. Okay. So this is the idea. I was sort of going through this stuff. Okay. So yeah. So there's a batch system. So the idea is good. You can see that. If you use these simple objects, and then you can build a script really easily. I found that I was doing that the same way again and again and again. So when you analyze a data set, I was rewriting a lot of the same code. And so the idea is we started looking at data sets from lots of different groups, which has been really fun, from maybe, 50 different groups around the world. And we'll share this kind of lightweight data set with results of first level analyses, and then you do group analyses and other predictive analyses and so forth. So I can look at all these different data sets, but I was setting up the same kinds of analysis with the objects over and over and over again. And so then I thought, aha, you should standardize the variable names and then standardize the system for loading those things and saving them so that everything is done the same way. So that's what this batch system does, right? So it's like a pipeline. So once we have the object tools, we can go back then to create a pipeline using those tools, and it'll run through a bunch of stuff and give you a baseline of analyses and results. Okay, so that's the idea for now. So did anybody actually get a chance to download them yet and install them? A few people did. Okay, so for everybody, yeah. What? Oh, this? Like that? Is that better? All right. Yeah, so this is the CanLab GitHub.io. All the toolboxes are here, but I'll just go through it now so we can do something. So this is the idea. What you need is SPM on your Matlab path, and you need our toolboxes on the Matlab path. All right, so I want to actually go through it and do it, because then I can start doing some of the demos and stuff. All right, so everybody has Matlab, I think, right? They have a trial version, okay. So next step, SPM, who's got it? Yay, all right, good. All right, and CanLab core tools. So the idea is go to the CanLab tool site. That's just the GitHub. Let's see if that works. Yeah, it works. So this is the CanLab core. This is this sort of set of basic object-oriented tools that you can use in other toolboxes. So I clone most of these things. You can clone it or download it, right? Cloning it is good because you can sync and pull a copy. All right. And then once you have that, in MATLAB, there's, this is going to be really small. I wonder if I can make this font bigger somehow. I don't know. I'm sure there's a good way of making the font size a lot bigger. I can lower my screen resolution, actually. That's bigger. Yeah, so there's this CanLab toolbox setup. So the idea is you go to wherever you want to put your GitHub repositories and then type that. And if it works right, it should download the other ones too. And there's 6 different repositories total that you might possibly want to use. And I put that in here. So I have this, GitHub repository set.
Do we need to add that first one to our path first?
Well, not necessarily. If you go to the main folder above that, so like if you put the core tools in that, wherever you put your repositories, like I've got this GitHub folder, right? So I think you should go there, and then it should find it, as long as the files are there. And then it should add those to your path. It will give you the option to download the other ones as well from GitHub, and then add all of them to your path. And if you've already got them in there, like, let me see if I do this.
If you go to CanLab core directory within CanLab core, and then.
Oh, is that right? I did it from the main one, but I don't know. You might be right. I don't know. We'll see. But yeah, I think right, because it looks for that, and it looks for the subfolder where the script is. But or you can drag and drop that into the. Oh yeah, that's right. You can drag and drop it into the command window too. Yeah. So that should, I hope, work. So for me, what it's done is it's gone through the different repositories and check them, and then they're all added to my path, so I'm okay. But yeah, you're right. If you're in the main GitHub folder, you have to actually specify where the file is first. So thank you. Yes. Yeah. Yes.
My version of Matlab is a little early, so they can't find JSON decode. Is there a place that we can get that?
Oh yeah. Which version of Matlab do you have?
I have 2016A.
Oh right. Okay. It's yeah, you might be able to get that from, well, I don't know. There's options, I guess. One option is that there's not that much that use that, like the batch scripts use it. Other things, like, it doesn't require it, so you can comment it out or just don't install that part. That's what I would do, or upgrade Matlab. Or you can pull like a version, but I think that gets kind of messy. Like, we pulled some of like the stats toolbox functions before from the web, and then it was great because then they, you didn't have to have the toolbox, but then it gets to be like, years later, I regretted it. Because, yeah, for various reasons. Because then you have all these old things, and yeah, let's plug this in. Okay, so does that work for people? Okay, yeah. And then if you download that 15 gigabyte pain data set at the same time, that's, yeah. Oh yeah. Oh, it's the connection to GitHub's not working right? I don't know. Yeah, it connects to download them, and then the next step is just adding them to your paths with subfolders, right? So if all of your expert MATLAB people anyway, or any kind of MATLAB people, what you can also do is like literally every one of these repositories is in GitHub. So here, if you go to this CanLab, I'll talk you through this anyway. You can clone any one of these things, right? To your folder, and then the only other step is just to add it with subfolders to your MATLAB path. So I can show you how that might work too. But while people are downloading, I'll tell you a little bit about what they are. So there's this core tools. That's the objects. The other thing, there's three things that are kind of linked together. The second thing is help examples. So this has some walkthroughs, like the first things I'm going to show you are on there as walkthroughs. And so it's basically, I did them as reports with MATLAB code and then figures and output in the file, so that it's kind of a static file. You can actually also save MATLAB interactive notebooks. So I love that, Jupyter notebooks are great. MATLAB has something like that now, it's kind of getting better. And so I saved one of them as an interactive notebook, but you can take any of the M files in there, which generate HTML, which then goes on the website, and then you can save that as an interactive notebook too, and do it that way. So that has the some walkthroughs, some stuff I'll show you, and then it has the batch script system for creating that sort of batch pipeline. And then there's this neuroimaging pattern masks, and that has a number of different patterns, predefined brain models, meta-analysis, patterns, and masks, and atlases. So I'll go through kind of more about how that stuff works. And this is, it's a whole collection. I'll show you really quickly what's in there. For example, let's see. And some of these things are things that the code uses, right? Because here's the idea. So here's some different atlases, right? So we've got like this, the Yo atlas, the Shen atlas, 7T subcortical atlas, the Fan brain netome atlas, the Glasser parcellation atlas, Neurosynth. Some of you might have heard of that. It's an obscure website. Maintained by, I don't know, I forgot who does that anymore. All right, it's TAL, it's TAL. This is Wolfgang Pauli's reinforcement learning atlas from the HCP data. Really good, actually. Awesome for subcortical regions. Like if you care about the habenula. I care a lot about neuroanatomy, actually, and there haven't been good tools for these, for looking at some of these subcortical areas and brainstem areas. One of Thomas Yo's new parcellation things, and this is a Frankenstein combined atlas that I made by munging all the other atlases together so that it actually covers the whole brain. And you can actually get, you not only have like all of the Glasser nature paper parcels, right, and separated left and right, and then different subcortical striatal regions. I'll show it to you later. You also have named brainstem regions. So if you really care about the PAG, or the nucleus tractus solitarius, or the dorsal motor nucleus of the vagus, or the nucleus cuneiformis, superior colliculus, inferior colliculus, whatever. Like a lot of those things are in there. So I basically constructed this thing where I tried to take the best stuff that I could find out there in a reasonable time frame, because I'm not a perfectionist, and put it all in there, right? It's a MNI 152, yeah. Yeah, that's the idea. And I realized too that there's lots of different spaces out there that are kind of similar, which is kind of a problem, But the Glasser is mapped to MNI space from surface space, and I think it's the one that several people, I think Chris was on that paper, right? And Thomas, there was this paper that I think Thomas Yo led that. It was a mapping of that into MNI space from surface space, from the PAL space. And that's like sacrilegious, I guess. But I don't care, because David Menison's not here. No, because we gotta, anyways. Surfaces are good too. That's a whole other thing. But I think this is pretty reasonable, And I think there's a lot of other sources of noise and variability, that we could talk about beyond those sort of differences. So I think the first order approximation of the space is pretty good. Okay, so that's the idea. It's got all these things. And so the idea is you should be able to take one line of code and say, give me any one of these atlases or any other atlas that you sort of plug in, and then down, separate a data set into all the parcels, let's say, right? So the idea is that's one of the things you can do. Here's meta-analysis maps, and I focused on our group, but I actually wanted to share this collection would be, stuff that's useful. So if you guys have ideas about other stuff that could go in there that is yours and you want to share, or somebody else's that they would be willing to have put up here, for redistribution, that would be great. I like that idea a lot. I haven't sort of gone out and done a lot of asking around for what can be redistributed. And then these are sort of defined models and patterns, again, focusing on stuff from our lab, but the Rosenberg, there's this paper by Monica Rosenberg and Todd Constable. They shared their model and said that we could redistribute it. So it's in there. So that's the idea, is to have a collection of these named models that have been published and that you could apply and validate and test in new data sets. And maybe I can talk a little bit more about that too. All right, so those are the these three things are kind of linked together. And I might merge them together at some point in the future. And then the other toolboxes, we probably won't get into too much. I might do a mediation demo if you want to see it. That's in the plan. But this is for coordinate-based meta-analysis. So that's sort of another thing. It's a standalone thing, basically. But it uses, all these things use SPM's image reading and writing functions. And that's why you need SPM, basically. But otherwise, they're independent. And then mediation toolbox does single and multi-level mediation, which is a really useful kind of analysis. And this one does robust regression for imaging. It's a pretty simple tool, but we've used this for our group analysis now for many years. So I think it's a pretty good alternative to standard OLS analysis. But I won't go, I'm going to focus on this sort of core tools in this interactive environment. Okay, so how are we doing with the download? Did it work? Kind of? Yeah.
So I'm getting an error that says something like the JSON decoder.
It's a diffuse version.
Oh yeah, do you have that? Yeah. Let's see. Here it is. This is the problem with toolbox demos, especially since I've never done this before. Okay, so it's totally scary. Is it looking for that? Yeah.
It's calling out.
So there's files. So is it adding? It's adding some things to your path, or nothing, or it's downloading them?
When I commented out that.
Oh, I see. Oh, okay. It did finish? Okay. Ah, okay. But it's put into what line did you get errors in?
I didn't get errors, it just said cannot clone repo, maybe private.
Oh, there's one. Okay, there is one that is. That's possible. If it's just one of those things, though, the neuroimaging pattern match should work. There's one here where it says this one. There's one private repository, which it should skip. So maybe it did work. Is that possible? No?
I'm getting different errors.
Oh, yeah.
It's not an error, it's just not moving past coding neuroimaging pattern masses. Yeah, it's at the end missing repositories, and it lists everything.
Oh, right. Okay. So if it lists them and it says it found it, that's cool. That might be because the neuroimaging pattern mass is a little bit larger than others. If it's hanging up, or maybe it's having just trouble connecting. Yeah, get the core tools, which you got then. Get the help examples in the neuroimaging pattern masks. So like those are the three.
The ones that did are, they have folders, but the neuroimaging pattern masses has been there for 10 minutes, and there's nothing in that folder.
Oh yeah. Let me see if I can download it too. It looks like it's download. It's 500 megabytes. That's the problem. I should probably stop that. Stop it. All right. If you do pull it separately. Let's see. So let's just say I want to add one of these things to my path manually. I can do this, like gen path, and then do this CanLab core, and it will do that. It'll add all the folders with subfolders, and then just do add path G. There, and then save path. So that's like what the toolbox, the thing would do for these different repositories. So let's see. So it might be a GitHub connection issue, or something else. I'm not sure. It went. Okay, cool. Relying on the web is a new thing for me too. I've never trusted anything that actually makes you be online, but now I'm kind of trying to get over the hump and do that. Yes.
Someone posted the error that I'm getting as well.
They posted what?
Posted on the Slack.
that function, so I tried commenting it out, but it didn't work, so I just hit it.
Oh, that's the JSON decode one? Yeah. Okay, cool. I should get the Slack. Maybe the coffee break. I should get on it. I can get on the Slack thing. I really like Slack, actually, for the lab. Except for it's apparently owned by a Russian oligarch. You guys heard that? Yeah. That makes me slightly worried, but not that worried. I don't know. Because Russia's our friend. Now. Anyway, all right, so that's that. Okay, so we'll give it a little bit of time. And then I'll check in and see if there are still other problems. All right, so that's that. Here are the different things that it does. So the CanLab Core Tools has a couple things that I wrote in terms of prediction and machine learning, but also, so right now there's some basic like object functionality for running basic models. I was using this other toolbox from Tübingen, the Spider toolbox, so we kind of integrated it with that for some things. But I think Matlab now has lots of different kind of off-the-shelf machine learning models. So we can use those. Some of them are already in there, integrated with this, and then it's easy to plug in other ones too. It's got the batch scripts thing I talked about. These things I talked about. And then there's some other tools, like things like hemodynamic response modeling. They're part of the core tools thing, but I wasn't planning on going over them specifically. Okay, so this is what you're doing right now. And I think then before the break, let me go and give you some slides. I'll give a little sort of mini lecture while we're getting everything installed on the pain idea of pain prediction and pain data. And this, you could potentially download it at some point. And if you do something cool with it, let me know, and we can talk about it. So that's there.
Zero parcellation.
Yeah. Yes. It's the, okay, yeah, so it's in, so basically when you add in the neuroimaging pattern masks, if you add this, it's this 2018 Wager Combined Atlas. And I want to show you how all these different things work. I kind of want to make sure that most of us, or all of us, hopefully are on the same page in terms of having stuff installed so you can try it out alongside me when I do it. But yeah, I want to go through that. But here, just sort of quickly, for those of you who are sort of already installed, you can do, there's this function called, so load atlas, for example. I tried to have these things that are kind of collections, you know, where it's a completed entry. So these are all things that you could load that are named. So like if I load, and I'm sort of putting the cart before the horse here, I guess, but maybe that's okay, just bear with me for a sec. So like the idea is this, you load atlas and I put in this named atlas. It's pretty flexible. It's all designed to be so you can put in anything you want to, but this is just for our convenience, right? When you do examples and demos and work with stuff in the lab, I have a small set of things that I want to do. So load atlas, and I've loaded this one, which is this combined atlas resampled to 2 millimeter space. For convenience, and then what I can do is I can use simple kinds of commands. So atlas is one of the object types, and I hope I'm not getting too far ahead, but there. So this is all the stuff you can do with atlas object. There's kind of a lot. That list is going to get smaller, because smaller is better, actually. So some of those things are going to be private methods that are not you know, as important. But and so you can do things, for example. Oh, here, I think I have this even open here. Here. So here I've loaded this, right? I can bring it up. I can do like orth views, and that brings up the SPM orth views. This is the other part of SPM that we use. So image reading and writing to nifty, and then the orth views is pretty handy. So you can see what the atlas looks like. Each of those is a, a parcel, right, in the atlas, and it's designed to handle, the sort of integers, hard-coded parcellations. And you can do like a montage of that object. And again, there's many other options for montages, and it's designed to be really flexible so that you can create custom montages any way you want to. This is, again, a pre-cooked set, right? So that's the idea, is it's this block set. So there's another object type that is an fMRI display object, and that object handles stuff like this, slices, surfaces, whatever, right? So that's a basic sort of toolkit, and then you can register montages with it. This is a particular collection of, I want those sagittal montages and those axial slices, put them in a figure, right? So there's another script that just, that has that sort of higher level organization. And then if you type the simple thing, like montage by default, this is what you get, right?
I have a question. Do you need the pain data set for the course of your lecture, or is that a data set that you play with afterwards?
That's like later, I think, yeah. The ones that for the lecture that I want to go through with you are less ambitious, because I realized that like it would take me like a long time to really download it and explain it and whatever. It would be a mess. So
we should use the bandwidth we have to.
No, not now. Maybe.
If you're downloading it
all right.
now.
You're part of the problem. Okay, I think we're taxing the bandwidth of the system here. Right. So yeah, so that's one of the things that you can do. If you do any object type, like atlas dot montage, now I'm going to get the help for that method, and it goes through what the options are for that, and what things you can add to it, and so on. So like, yeah, force the colors to be symmetric across left and right, so that you put them up, stuff like that. Yeah, and I can do things like, remove. So this O2 is a variable that's an atlas object instance, and I can, oops, oh, I didn't save it. I should have done this. So let's see. Okay, so that's a different kind of montage set. It's just a different set of slices, right? Again, pre-cooked, you can make your own. So it's going to add those. It's going to return the output in this fMRI display object. And that is going to let me do stuff with this, like add a new montage, add blobs, remove blobs, whatever. So that then you can reuse the figures, or have a whole registry of multiple figures with different montages and some surfaces, and then add and remove blobs as you like. So that's another thing. Now I've got this atlas object, and now I can do this, and I can take off the blobs. There, they're gone, and now I can add some more blobs from something else. So that's just a kind of a quick idea about that. Let me check in on if people have it installed okay. Okay, good. Who's still having trouble? Either nobody, or else you're on your email. Okay.
That download really helped.
The what? The which one did?
I was downloading all that data.
Oh.
Blocked out.
Oh, I see. Yeah, the download. Yeah, right. Yeah. The bandwidth thing. Oh, sorry. Okay. Yeah, go ahead, and then we'll go back to you. Yeah. Right. Yeah, and then the help examples. The help examples just has like the walkthroughs has some walkthroughs that I'll show you, and then the batch system too. So that's pretty small. I think it's pretty lightweight. The pattern masks are the meaty ones. So I kind of struggled back and forth across the years with like, what do you store in what kinds of repositories, because they're, you don't want it to be too big and unwieldy, so I try to keep it all pretty lightweight, but yeah, so it's a balance, I guess. And oh, that's a bummer. Yeah, so oh shoot, some of the montage things might need the image toolbox. That's too bad. Yeah, I was a little bit afraid of that. That was my fault. Maybe we can we add it with the trial, do you think? Yeah.
They respond as quickly as Google does.
Yeah, they'll do like a free trial for a month, right?
Yeah, they asked me what toolboxes to put.
I know, and I told you, and I thought about the image one. I'm like, I don't think we need that, and I didn't go back. I need to, that's a problem. Sorry, I better have it check all of them. Problem is, my university has all the toolboxes, and so I have to have another thing that goes back and checks. So that's a work in progress. And by the way, how many people actually have Matlab through their university or something? And how many people would actually have to buy Matlab themselves or something? It would be a problem. Yeah? Okay. So, I don't believe you guys back there. Stanford doesn't have Matlab. They don't allow it. All right, maybe you're right. I don't know. No. Yeah. Anyway, just wondered. But yeah, so we, I get it through the university. So that's helpful there. Okay. Yeah, so we might need the image processing toolbox to go through some of these things. And it's good. If I find that out, this is, again, a kind of a new thing for me to try to do this and try to share it more broadly. So I am happy if you tell me about issues like that. What we can do is either go back and remove the dependency or just make sure we check and add that. So let me know if problems come up. Okay. So before I go on to this sort of pain motivation thing, let me go back to my plan here. And so here, okay. So actually, I think this is on the website too. So if I go back to the GitHub site, we're doing setup. We went through what the repositories are. That's another view here of what they are and which ones to get. This is a little bit more about the ideas of interactive analysis and the types of objects. I'll come back to that in a second. Here's some walkthroughs that I wanted to sort of go through to orient you. And so they're on the GitHub.io website. All of them are in the CanLab help examples repository. So that for every one of these things, what you see is, let's see, if I go to this, where's my CanLab help examples? There it is. Okay, cool, there, okay. So then there's some docs, which is redundant with the help on the website. There are these help files, and you see these. I've really started creating this, and this is part of my effort to really make this stuff usable and understandable and document it. So you're my guinea pigs on that. So these walkthroughs are starting to be numbered. There's relatively few of them, but I want to add more and make sure there's a whole sequence of stuff to go through, right? The example datasets are all included. So. Well, we did this, the installing tools one, we just did that. This is basically what you've been just doing. So we're good there. And then the next one, and so you can see here, load a sample data set. So let's go through that. And then what you can see is, this is super simple, I hope, if it works. Then it's here, and so then you see the different sections, and then the results and output, that you should see. So a sample data set that I want to use to go through a lot of these things is this emotion regulation data set. And it's one of the contrasts from a now relatively old study that I published in 2008. So, there. And there's all this stuff is to make it look better than HTML mostly. So you can do this, and you can do it as an interactive script too. Actually, I'll do this. Watch. Let's see. Let's save it as, and see if it works. This Matlab line code. that's the Matlab version of the IPython notebook. How many people have used that before? Okay, a few, but not everybody. All right. So yeah, I'll save it in here as that, and then we'll see if it works. All right, look at that. So this is really simple. I just want to sort of, there's a lot of instructions that we've already gone through. Here's the original paper. So this is a data set with 30 participants, and it's an emotion regulation study. So each one of those 30 images from one person is a contrast between looking at negative pictures, aversive pictures, and then reappraising them by generating a positive meaning, like, this is going to be okay. And then just looking at the aversive pictures. So they're matched sets. Right? So it's supposed to basically capture some activity related to emotion regulation. Again, I wanted the point of entry to be really easy. So this is it. There's this function called load image set, where you can load a whole bunch of, or several different named collections of images. And so we have the sample data in the CanLab core. These data are nifty files, or whatever they are, analyze image files in the CanLab core toolbox. And then when you do this, what should happen is it should load them into a data object. I'm not sure why I get those warnings actually at all, but here, let me see, continue. Okay, so now it says it loaded these images. Okay, it's going to plot them. Oh yeah. So here's what it did. So the first thing that we'll do is just look at this. I don't think it's popping up in the Matlab window at all, is it? It's just, yeah, it's just there. All right. So I might just do it outside. So that's an interactive script, but just so we can see it better. What were they called? What was it called? So okay. So what we've done is we loaded this set of images into this data object. And that's kind of what it looks like, but one way to interact with this thing is to plot it. And so if I use this command plot, instead of Matlab would normally create a line plot or something, right? But for this object type, this, which is an fMRI data object type, which contains this collection of images loaded in, it does this. So it shows me several different plots, and then the orth views I can surf around. And what you see over here is just the mean image, so you can see what it looks like, the standard deviation. Now this is a group analysis, one image per person, so we can immediately start to look for problems and just know what they are and then say, I don't know what to do about that. Or maybe we can go back and fix it, etc. But you know, it is what it is. This is, so you can look at the standard deviation across the subjects, right, at every voxel. And why would the standard deviation be like high here around the edge? Yeah, or between subjects, because yeah, thank you, but yes, you're right. Every subject is a reappraise minus look, right? So it's their reappraisal related activity. But right, if what? What about the field map? Do we use it? Not in this case, no. So we didn't. Yeah, we didn't do any unwarping. Yeah. Yeah, so the subjects aren't lining up very well, right? Potentially, around these areas. So yeah, high standard deviation. So you can start to see some of these things are in, this is the, what's it called, posterior cistern above the cerebellum. You know, so you can see high variability there. And then the mean over standard deviation. So this is the simplest version of Cohen's d, effect size per voxel, maps for that group analysis. So we can potentially diagnose problems. I've seen a lot of things where, you know, the brains don't line up. People normalize brains in. They don't really look at the brains afterwards and to see how the normalization worked, and then they're really variable. And like the top of the brain is up here or down here. Now that's much bigger than that difference between the, you know, surface and MNI, you know, native surface and MNI surface, stuff like that. So I worry about that stuff sometimes. It also shows you this kind of plot of the data. And this is, again, another way of exploring, like what I really, you know, the data, seeing what you got. And one of the things I've wanted to do more of since my first failed visual cortical activation experiment is kind of get in there and, you know, see what you're doing easily. And I figure if you can do it easily, you'll probably look at it. And if you can't do it easily, you probably won't look at it. Maybe you guys all will, but some people won't. And so, so this is one guess as to what a sensible set of plots is. If you have ideas, you know, for what we should be plotting, that would be awesome. And the idea is that it shows you this. This is voxels by images. So it shows you all of the data. Each row is a subject. And what you can see here is that subject 6 is really bright and subject 16 is really blue, right? So they basically has a global shift in these contrast images, right? So you can kind of see that instantly there. That gives you something to think about. I see this a lot. So as I've tried to look at data across, you know, 50 different labs or whatever, more from around the world, not all these data sets have this feature, but a lot of them do. You know, and think about maybe task-correlated head movement or something that happens to correlate more with the task for, you know, more positively for the task for one subject, negatively for the other subject. And that, basically, that resulting artifact shows up everyone's brain, in large areas of the brain. I'm curious about how many people look at these kinds of things in their data sets and really think about it and try to mitigate. Yeah. Just wondering. Yeah. That's a single voxel intensity, right? So every image is an average image for reappraise minus look. So that's the contrast image for that subject that we care about, right? And then that row is every voxel, right, for that subject. If that makes sense, yeah. Yeah, so that's interesting. So if you can see this, I'm curious, what do people do about that? Yeah. This is all after. Okay, maybe I should have gone back and explained better about the study. You know, so here's kind of where this comes from, and thank you for that. So it's the whole. So we did the whole like standard SPM first level pipeline for every subject, right? So every subject has multiple conditions, including looking at neutral pictures, looking at aversive pictures, and reappraising aversive pictures, right? So then the first level model is, you know, beta images or COPES and FSL. They're regression, you know, slope images, right? And then we take those for reappraise minus look. So each of those is the average across trials when they're just looking at reappraising, right? And then for that subject, we'll subtract them, and then we get this contrast image. So that's what you would put in, and then we collect those across all the subjects. So 30 contrast images. Now the standard kind of simplest possible group analysis you could do with this is a one sample extent across the subjects, right? So is there activity greater for reappraise than look on average for every person in the data set? Does that help? Yeah, so they've been pre-processed. You know, we put in the motion parameter estimates as covariates in the first level and various things like that. You know, but this is really the result of all of that. You know, whether it was good or bad. You know, modern or old. Yeah. Yeah, so that's one thing. I'm just curious about what people do. If you see these kinds of issues, what do different people do about it, if anything? Chris?
I think you have to be careful here because this is an outlier again. That track down if there is a low-level raw data quality metric that actually can predict those outliers here, and use those quality metrics a priority in computer science to remove certain runs from your analysis.
Yep.
Without looking at the
Right. So if you start dropping all this, like the blue subject, because it's blue and it's deactivated everywhere in the brain, I've now got to buy a sample. So I'll end up with whole brain activation. I see whole brain activation very frequently. It's been really instructive for me to look at these things across many data sets. It's been really fun. You know, I have a whole collection of them where we're just looking, and some of them are turning into papers, and some of them aren't, and who knows. But yeah, and it's really pretty common to see whole brain activation or deactivation, especially at the individual subject level. And you're right, if you can sort of figure out a principled way of preventing that from happening in the first place, that's good. It's probably not, it can't be real, it's not real signal, but you can't just start dropping subjects because you've looked at their contrast images and you didn't like it, you know, or they didn't fit your hypothesis. Yeah, for sure, yeah.
How all processing steps work. Like these were
Yeah. Right. Yeah, along those lines, one of the things that we've done is look at the correlation between the task regressors and the estimated movement. You know, so how much, and what are the I'm getting ahead of myself again, but what are the variance inflation factors? So the variance inflation factor is a really simple number where you can compare what would happen with all these different movement covariates and without. And if the variance inflation factor goes up, that means this thing for that person is this slope, you know, is really variable across, you know, because it's correlated with the movement estimates. That doesn't give you a complete answer, but it's something, right? Yeah, so there are reasons that you might want to then downweight cases or you know, in principle on that, but that's a whole other discussion. I think it's quite complicated because you can end up, again, biasing your sample. Yeah, you had an idea, didn't you? Did you have a comment or idea? No. Okay. Yeah. So I don't know. I see these things. Just so it's a basic idea of a basic plot, right? I have a regression walkthrough, which I might be productive to go through after the coffee break, too, where you think about these choices, you know, and what to do about them and stuff like that. But for now, this is the covariance across the images. So what should it look like? Well, if you have equal variances, you know, assumption basically, if you have equal, if all the subjects are on the same scale, then the diagonals should be bright. That's the variance for that image. You know, and then the off diagonals should be dark or blue. They should be either independent or basically with some low uniform correlation if there's a real task related activity somewhere in the brain that's driving that. So that's just a picture of what that looks like. So some of these subjects, like this 16, is actually really high on variance because they have whole brain. Global means with this spatial standard deviation across the brain. So you can see the time series, you can see subject 16 here and subject 6 there. Mean versus standard deviation, that's a plot that can show you something about the image scaling. So if you basically take an image, especially for time series images, not as much for these kinds of images, but if your images, whenever you do an analysis, you assume your images are on the same scale, like fundamentally. And if they're not, then you end up with errors and with other kinds of artifacts that make p-values invalid. And so if you see this, I've seen an awful lot too. If the mean and the standard deviation of those images are correlated, or the standard deviations are voxels, then what that means is that that's consistent at least with a sort of a random multiplicative scaling factor being added to those images. So I've seen a lot of time series data from some scanners, not from others, et cetera, where the correlations are like 0.9. So clearly, there's something happening. There's a process that's happening that's affecting the mean standard deviation of the image in proportion, like you're multiplying that image by some value, right? I don't think there's always a simple solution for these things, by the way. I didn't want to go off on this deep end. I just wanted to show you the tools. I don't think, but I don't think there's a super simple solution, but I'm quite interested in it. And if you could divide, if you divide by the mean of each image, for example, and that's a global scaling, but that can also produce other kinds of issues, right? Some people call them artifactual deactivations, but you're changing the interpretation of images, right? Because it's now relative to the global mean. Stuff like that. What do you think, JB?
It's not more than this.
Mm-hmm. Yeah.
And then obviously, if you have like some other kind of data, place data, question data.
Yeah. Yeah. Mostly I look at these things in some data sets, I go, ooh, that looks really bad and interesting. And then I don't do anything about it. And then we just, it's mostly noise, or sometimes you might mistrust an analysis, right? And you say, oh, this data set's wonky, But mostly I'm not doing anything because I want to figure out good things to do on average. And so I'm looking at maybe like 1,500 subjects from 50 different sites, let's say, right now, and thinking about it. So this is one thing that hackers can do. But what is there a good, what do you do, right? And okay, this is an idea. This is an estimate of what the basically normalized Mahalanobis distance, which would be how similar is each image from every other image. And so if you have an image that's really different, it's going to stick up. It's going to have a really high value on this, and anything that's high and positive is flagged automatically as a potential outlier. In some of the code. So yeah, this can tell you about whether you have some image that's just really not like the others. Stuff like that. So that's the plot. Right? When you say plot, that's what you get. Okay, so where are we here? We've loaded a data set and we've plotted it. We're done with that demo. That was the goal. Just to get that sample data set. Now we'll go on and do other stuff soon, potentially progressively more complicated or whatever. But I think this is good. And some of the examples and walkthroughs will use that data set. I've also got a couple of different pain data sets that are pretty lightweight that we can do demos with. So I want to go through like the basics of how to do stuff with the objects, so then you can like have a launching point to be creative and do other stuff. I want to go through a couple of analyses like this, where there's already existing walkthroughs, and kind of talk you through them. And then we'll get to like some multivariate predictive analyses using some of those example pain data sets. Again, pretty, we have a sort of preset standard thing that works easily, which I think is great because that's then a benchmark. So then if some of you have other analyses that you think are better, more predictive, you could do different kinds of feature selection, you could do various things, right? And then and deep learning, maybe that's better. And then we have really good benchmarks for the pain data. So that's actually pretty nice. So if you do this with any of these example data sets, which are actually pretty good data sets, or with the big 15 gigabyte, 25,000 image data set, we have really good benchmarks for how well these things work with the models that we've been using. And so and across many studies. And so if you have something that works better or whatever, then we can tell. So that might be interesting. All right, I'll come back to a little bit more motivation on the pain later. But for now, I think it's exactly time for a coffee break. Isn't it? 10:33. All right. That was the most non-lecture lecture I've ever given in my life.
Oh, yeah, just a second. Don't go anywhere. Just a second.
Yeah.